Hello everyone, Dr. Gilmet here, and we are talking about the chi-squared test for independence today. All right, so when conducting research, we often want to see if two categorical variables are related or if they're independent of each other. In other words, we're looking to see if one variable impacts another variable. So this type of research calls for a test for independence, and it actually requires the chi-squared distribution. So in this video, I'm actually going to show you how to conduct the test for independence. Well, how does it work? Well, today in the Arrowverse, there is a compound called mirakuru, all right? And in the show, it's used to create super soldiers. Serum like this can have many effects on its recipients. So how do you test for which effects you can expect? Like, does it make you stronger? So you have two categorical variables with which to test. So the independent variable in this experiment is took mirakuru and did not take. And the dependent variable is normal strength and super strong. So we need to test for independence to determine if the serums affect strength in subject. So let's dive into the test. But before we do, I want to talk about what we're actually going to cover in the test. I want to be clear what we are and are not going to cover. So this is a video about how to do the test for independence and using the chi-square distribution. I am not going to discuss the properties of the distribution. That would be for another video. I'm also not going to cover Fisher's exact test. I'll do that in another video, but for length, and this is already going to be pretty long, I am choosing to focus on the standard test for independence using chi-squared and the maximum likelihood. Additionally, I want to show you what's happening behind the scenes. Thus, I am actually going to use Excel to perform the test. This allows me to show you what's happening and allows you to replicate it without the need for special software. Most people have Excel on their computer already. Statistical packages often have a couple of buttons or lines of code that produces the output, and that obscures everything that's going on behind the scenes, all those calculations. They can also be pretty expensive. SPSS is in the thousands of dollars. All right. So back to our experiment. Will I get super strength? Let's say that we randomly assign 50 participants to two groups. One that's going to receive mirakuru and one the placebo. Then we observe the following after a deadlift test for strength. Okay. So these are our actual observed values. Are they just strong or did they get super strong? Did they not take mirakuru or are they actually mirakuru enhanced? Those are our two variables and the two factor levels of each of those variables. We're going to see that without mirakuru, 20 of them are strong and only 5 of them are super strong. Maybe genetically or because of bodybuilding experience, or maybe they're metahumans. But that's the 25 that are in our placebo group. For the mirakuru enhanced, we see that 5 of them are strong and 20 of them are super strong. Okay, again, the 25 assigned to that. And maybe these 5 are only strong because, the mirakuru didn't work on them or didn't work on them as well. For a total of 25 strong and 25 super strong. Now, from these observations, it seems pretty clear that the drug impacts strength. This is actually on purpose, so the results are very clear. I also wanted to make sure that I had at least 5 in each of the other categories, because that's appropriate for a chi-squared test. And so everything is pretty balanced. This allows us to focus on the mechanics and what's actually going on and not get distracted by details. All right. So off to Excel. All right, so here we have that table that was in the Word document with our results. Now, if this is what we observed, what did we expect? And this is the big thing in the chi-squared test, is you want to know what would we expect if there was no dependence, okay? And the way we do that is we're going to use these marginal values over here to determine how many we would expect to be strong and super strong given the number of people who took mirakuru and did not take mirakuru. All right. So over here, we would expect the equal sign indicates that we're getting ready to do a calculation that for no Mirakuru, what proportion of their that did not take Mirakuru times the total number of people who, this is strong, ended up being strong. Okay, so the proportion here is 12. All right, now for those that we expected to be super strong, again, what is the proportion of people who didn't take Mirakuru, and then what were the total number of people who ended up being strong? So this gives you a marginal value here that allows you to determine that. Now, we would actually expect if there was no dependence that we would actually have equal numbers, because we have equal numbers of strong and super strong. We would expect equal numbers of strong and super strong if there was no impact for Mirakuru. So that's what these expected totals are telling us. So here, we're going to do the same thing. The proportion that took the Mirakuru times, and again, strong, the number of people who were strong. Oops. All right, so I accidentally clicked on just this one, and I wasn't supposed to do that. Remember, what we wanted to do is the total number of people who were strong. Okay, and again, here, what we're going to do is the same marginal total times this total number of super strong. And we can see that this is a very square matrix, equal numbers. We should find equal numbers of strong and super strong because there were equal numbers of people that showed that. And there should be equal numbers of strong and super strong because there were equal numbers of people, participants who took the Mirakuru and did not. So that's why this is square like this. All of these. This is what we would expect if you had equal numbers of strong and super strong and equal numbers of participants taking the Mirakuru and not taking the Mirakuru. And again, this was done because we wanted to have at least 5 for the test and to understand what it was that's expected when things are independent. So this makes things absolutely easy to understand. All right, so now there are 2 ways of doing this. There's the standard chi-squared test, all right, and for that you have the observed minus the expected squared divided by the expected. Hopefully you understand this as a variance, right? If you take the observed minus the expected, you could get a negative value. So the squaring that gets rid of that, and then you divide it by the expected, and that gives you the variability that you would see. It's kind of like a chi-score, if you will, a standard deviation, a variance among them, all right? So for here, for the strong, what we're going to have is equals, and we're going to put our parentheses in because you can see the parentheses here, and we're going to square it at the end. The observed, a strong, no Mirakuru is right here, minus the expected value of strong, no Mirakuru is here. We're going to actually square that, and then we're going to divide it by that expected value, okay? Now, when I hit enter, I get 4.5. Now what I'm going to do is I can actually take this and I can drag it over here and down. All right. And you'll see that we have these values right here. Okay. And so we actually are getting a chi-squared of 18. Now, if you think about this in terms of z-scores or f-scores, right, this is 18 deviations away from the center. This is very statistically significant, okay? And that's because we obviously have a dependence here, right? And so this is just an exaggerated example. Now, for the degree of freedom can be calculated, and this is actually pretty easy, right? What you would do is you would just say, hey, look, I have 2 factors here, And then I always subtract 1 because this is a degree of freedom calculation. And then I have 2 factors this way. And then I'm going to subtract 1 again. And then I hit enter. All right. So this is very much like a 2-sample t-test, right? Where you have to subtract 1 from the total number of observations in each sample. So now for the chi-squared. The chi-squared is just this value right here. Now to calculate the p-value, the probability of this happening at random if there's no independence, we're actually going to do a chi-squared distribution, right? We're looking at that chi-squared distribution. But this is a right-tailed test, okay? Because we're actually looking to see if it increases strength. So we're in the right tail here. So I'm going to use this particular function. The x is actually the chi-square value. And then the degree of freedom was the 1 that we calculated up here. And when I hit enter, it's 0. And that makes sense because 18 deviations away, a chi-squared score of 18 is really, really large. All right. Now for significance. I'm going to throw this in here because I saw this done a couple of places and I really liked it. I'd like to use an if statement. And the logical test is if your p-value is actually less than your alpha, then you have significance. Yes, I have significance. If that's not true, then you do not have significance. There is no significance. And I saw some people type this in. I saw some people put reject or do not reject in here as well. But this is actually what you're doing to determine significance is do you actually have a p-value smaller than your alpha? And so when you hit enter, this is yes. Now, if this p-value had actually been 0.10, you would have gotten a no. Okay, but because we actually got significance here, there's the yes. All right. Now I'd like to show you the maximum likelihood test. It's basically the same thing, except we're going to use a slightly different formula. In the Real Statistics website written by Charles, I can't remember Charles' last name right now, but I'm going to leave a link to the website and that because he did such great work, and this is where I took some of this from for the Excel. He talks about this maybe being a better estimate. And so I just wanted to really quickly show you for the strong, right? I'm going to do equal. It's now the observed, right? Again, strong, no Mirakuru, times the natural log of the ratio of the observed to the expected, okay? And so we're going to get this 9.401 here, okay? I can go ahead and again copy that across and down, and we'll see that the maximum likelihood is about 19. Again, here's my alpha, my level of significance, my degree of freedom. I actually did a little count thing here. There's the 19.27. Again, it's a little bit further away, so the p-value is still 0, and so it's still significant. But it just shows you it's a tiny bit different way of doing it. And again, this isn't about the math. It's just this is the typical way that we see it done. And then this is a different type of test for maximum likelihood. They give you pretty close to the same error answer. But because they're calculated 2 different ways, this one may be more appropriate in certain circumstances. All right. Now, what about genius level intellect? We were focusing on strength, but this is a great question. Suppose we give all the participants an IQ test and categorize them or average or genius level based on the results. The following is a possible outcome, right? That there were an average of 12 of them without, of average intelligence without, and 13 with, right? And then 14 of them with average intelligence and 11 of them with genius level intellect with the Mirakuru, okay? Because remember, these are bad guys, super villains, right? And so obviously, you got to fight smart bad guys. Here, it looks like the serum makes no difference. We have nearly equal numbers in all of the categories. But to confirm this, we could perform another test for independence. And so we're going to go back to Excel, but simply discuss the results. So here in this second tab over here, when I click on it, again, here are the observed. I've already done the proportions. Here you can see it's not the same. I have 13, 13, 12, 12. And that's because I had 26 with average intelligence and 24 geniuses, okay, with equal numbers of participants. So this is a little different. It's not quite square. So what we see here is when we do the chi-squared test, right? And again, I'm just taking the observed minus the expected squared divided by the expected, and I get 0.08. So my chi-squared is about 0.32 deviations. Again, because it's a 2 by 2, there's 1 degree of freedom. My chi-squared is 0.32. So that gives us a p-value of 0.571, which is certainly not less than 0.05. So we do not have significance. In fact, we would see something like this in about 57% of samples of size 50. Okay, we would see this kind of a distribution. And again, you can see that the maximum likelihood is very, very close to the exact same answer. And therefore, we get the exact same p-value and result at least to 3 decimal places. So it doesn't look like it impacts overall genius level intellect. Now, we could change this a little bit. We could say that this was 21 and this was like 4, right? And we could have said that this was, 20 and 5, right? Because maybe geniuses are a lot less likely. And so we would actually expect way more average and way less geniuses because of the way this is distributed. See how the 41, 49, 50, see how this proportion remains the same and this proportion remains the same. I'm just equally distributing them for the expected. And here we actually get 0.713 and 0.713 and still no significance, right? So even if we had a more average to genius spread, we would still expect this. Now this 4 could be problematic because it's these 4.5s, these expected cells being less than 0.5, we might need to do Fisher's exact test. But again, I'm not doing that today. Final thoughts. I hope you found this helpful to your understanding of the test for independence and how to conduct an experiment with categorical variables, because often that's what we have. I need to give lots of credit to Charles Zenowitz, as he runs the website realstatistics.com that helped with the Excel formulas. Okay. If you would like to see videos in SAS or R, or if you want to see the Fisher exact test for observations of less than 5 or for 2x2 tests, please leave me comments down below about what helped and what you'd like to see. As always, as this video helped you, leave a like, maybe subscribe to the channel. I'm actually going to be working on more content in 2021. My workload professionally has reduced, and so I really hope to make more videos in the future. I'm super excited about that. And if you're super excited about it, that makes me happy. And hopefully this video made you happy. Until next time.